Having spent much of her career at undergraduate-based institutions, Professor Etter is fondly remembered as an educator, mentor, and supporter of early career scientists, and that gave rise to this award, which goes to an investigator who has made outstanding achievement and exceptional potential in an area of structural science at an early stage in their independent career. So very appropriately, this year's awardee for the Margaret C. Etter Early Career Award is Professor Julia Zaikina, and I apologize if the pronunciation isn't correct, of Iowa State University. It was close? Okay, good. Glad to hear that. Professor Zaikina is at Iowa State University. She completed her graduate training in Russia and Germany before coming to Florida State University and then University California, Davis for her postdoctoral work, and subsequently moved to Iowa State in 2017 for her independent position. Dr. Zaikina uses an impressively broad set of technical approaches, both theoretical and experimental, to study complex intermetallics, which exhibit polymorphism, stacking faults, and complex twinning. And I look forward to learning a lot more about what those are in the next hour. While we missed the opportunity to meet you in person, Julia, and discuss your work and career in more depth, I am delighted to offer you our warmest congratulations on behalf of the ACA, and I look forward to hearing your lecture. And so I see you have your screen shared, so I'll turn the floor over to you.
Great, thank you so much for the kind introduction. And I would like to start by saying thank you, American Crystallographic Association, for recognizing the research in my group. Thank you for organizers to give me this chance to talk about the research in my group. And it's particularly special to me since among the previous recipients of this award, there are several prominent solid-state chemists. So I'm in such a great company there. So today I will be talking about how we can discover new solids containing alkali metals by using predictive screening, facile synthesis, and in situ studies. And I would like to acknowledge people who did all the work. I would like to, I would like to thank my group pictured here, for joining me in 2017, helping me to build up the lab, and it was such a pleasure to see you, developing as a scientist and also sort of develop with you as your advisor. So I will be talking about the project which is performed by two graduate students, Tori Cox and Gurab Kaskar, and very talented postdoctoral scholar, Dr. Vladimir Gvozdetsky. So we are very fortunate to have a very impressive list of the collaborations. So we have collaborations among chemists at Iowa State University, as well as a physicist. Iowa State University is a very special place because we do have national lab on campus. Ames laboratory is located on ISU campus. And this gives us a lot of opportunities to interact and collaborate with researchers and scientists at Ames lab. We also have collaborations with Argonne National Lab, as well as the Oak Ridge National Lab, and we do have several collaborations in Europe. And financial support comes from a National Science Foundation, the NSF Career Award from a DMR program. So the research in my group can be divided into the two major parts. In one, we are using innovative diffractive solvent route to synthesize functional oxides and sulfides. And I will be not talking about this part today. In the other part of the research, we use hydride precursors for synthesis of new materials. And here we are looking at the two classes of compounds for now, even though this synthesis method can be extended to other classes as well. So for now, we are focusing on borides containing alkali metals and also antimonides containing alkali metals. So as a solid-state chemistry group, we are interested in this structure-property relationship because the structure of the compound determines its property. That's why we want to really understand the structure of the compounds at atomic level. We want to really pinpoint where the atoms are. That's why we do use a variety of the diffraction techniques listed here to the right. So we use powder X-ray diffraction, and we have several diffractometers on campus, single crystal X-ray diffraction. But we also want to see how our crystalline materials transforms with temperatures. That's why we use high temperature powder X-ray diffraction, as well as the low temperature diffraction, which is available for us at Argonne National Lab. And then with the neutron diffraction, we can locate the position of light atoms in our structures, as well as determine magnetic structures of the materials we synthesized. And for the materials which lack periodicity along one particular crystallographic direction, also my light went off. We use scanning transmission electron microscopy, as well as per distribution function, to really understand the structure of the material of our materials even better. Now, as a synthetic chemist, we also have another way to modify the structures of the materials we made by choosing the appropriate synthesis methods. And that's particularly important because by using different synthesis methods, we can control the purity, we can control the particle size, the crystallinity, particle shape, amount of the defects and dislocations. And for certain materials, that's what determines their property. And I want to show you the most recent example from our group, even though I promised not to talk about deep-effective solvent project at all, but this is the very recent result we obtained. So the lanthanum cobalt oxide, which is a known oxide, but when we prepare it via deep-effective solvent route, this material now features a lot of oxygen vacancies, which manifest themselves as those dark stripes at scanning transmission electron microscopy image. And thanks to those vacancies, this material behaves as a really remarkable electrocatalyst for water oxidation. So as a solid state chemist, we are targeting new compounds, but not. We also want to see those compounds to be used for the particular functional material. So this is how we envision the material discovery. So we first want to discover our material within the computer. So we want to design the electronic structure, which gives us the desired property, that's the crystal structure. Once we have this kind of prediction, we know what composition of the material we want to target, then we go to the lab and try to synthesize it. So structure determines the properties. So the next step is to determine the crystal structure quite precisely, and then measure the desired property. And then if the property is not what we expected, we then go back to the computer and see how we can modify composition to give us the desired electronic structure or to a desired property. And then we go back to the lab and synthesize this new material. So of course, this is a very idealized way of the discovery of the new materials. And the cornerstone here is the synthesis, because oftentimes it's very difficult to synthesize the materials, especially if you don't know their composition and their structure. But even if we have an idea about the composition, still there are several difficulties associated with the solid state synthesis. And I want to convince you that it is solid state synthesis. It is a very challenging way of synthesizing the thing by showing you those four papers from 90s. So solid state synthesis, because we don't have this degree of the predictability similar to organic or metal organic synthesis. That's why the solid state synthesis was considered as much as art, as science. Because we don't have the rational design for the compounds we make. The compounds discovery is a pure luck, and so we have to explore our synthetic phase space, by trying different compositions, synthesis temperatures, dwelling time, heating rates, until we have the positive synthetic outcome. So this was until recently where we start. So I feel in the recent 10 years or so, there was a paradigm change in the way we think about solid state synthesis. So these days we have a certain computational methods which allows us to predict whether the particular compound is stable or not, already way before we start making it. We also now have high temperature powder X-ray diffraction, which is which became more available for the researchers. So this way we can track what is happening with our materials when we increase the temperature, because solid state synthesis generally happens at several hundreds, 1,000 degrees Celsius. Yeah, we need very high temperatures. However, for certain materials, it's the choice of the precursor and heating method which matters. So we need to be very vigilant in this choice. And actually, I want to contradict myself here by saying that sometimes we really don't need to use high temperatures for the synthesis. So soft chemistry methods come into play. And in principle, all these successful strategies can be incorporated all at once, because we can predict the materials, we can use high temperature X-ray diffraction and unconventional precursors to discover the materials right away. And the challenge here is that in general, we do need high temperatures for solid state synthesis, because we start by mixing several solids, and the diffusion is very slow. So by increasing the temperature, solids transforms to liquids or sometimes to gas phase. So this increases the diffusion, this increases the rate of the solid state reactions. But the problem is that by going to high temperatures, we stabilize the thermodynamically stable products. And oftentimes those compounds that have been already known for decades, they are what we call boring compounds. They have been studied quite so well. So by going to high temperature, we're going to miss some of the exciting kinetically stabilized compounds. However, the necessity of high temperatures stems from the low diffusion between the solids. And we also have an example from research in my group. So for instance, if we mix sodium, zinc, and antimony, 3 elements. Zinc and antimony can be powderized, sodium metal cannot. It's easy to make this 1,1,1 compound, and it has been known for several decades. However, if you want to shift from these compositions and see whether the compound with this stoichiometry exists, if we try the synthesis from elements, we would have a lot of sodium, zinc, antimony 1,1,1 compound previously known. So the diffraction peaks here are marked with stars. There will be also binary compounds and some of the low intensity diffraction peaks, which suggest that there might be another compound present. However, if we have several phases present in the sample, establishing the structure of one of the compound becomes particularly a difficult task. So we really need to have to find a good synthesis method which allows us to target specific composition. So if we narrow down the systems we are looking at toward the systems containing alkali metals, that brings additional challenge. Because in the traditional solid state synthesis, we would mix elements. and then add the alkali metal. But because alkali metals, they are soft, ductile metals, so they cannot be really mixed with the rest of the powdery precursors. So we would need to add them in pieces, and then we really need to go to high temperature so the alkali metal melt, which allows for it to mix with the rest of the components in our reaction mixture. But even at high temperature, the melt would be inhomogeneous in composition. Yeah, so while those alkali metals are commercially available precursors, if we use them for synthesis, we would need to go to high temperature to allow for them to well mix, and it also entails long duration of the synthesis, low kinetics, and oftentimes we need to perform our synthesis in multi-steps, which basically takes time. So in my lab, we switched from using alkali metals, elemental alkali metals, to their hydrides. And hydrides, they come as powdery material, where resembles the table salt. Of course, it is. They are very air sensitive, so we handle them in the argon-filled glove box. But nevertheless, they are powdery, so they can be mixed well by the technique called ball milling, so they can be mixed well with the rest of the precursors. So this way, we already start with very homogeneous reaction mixture, so we really don't need to go to very high temperatures, and our reactions are always faster. Yeah, so the traditional solid-state synthesis reaction takes place, several days, oftentimes several weeks. In our case, it's several hours. So you put your reaction into the furnace in the evening, and you already would know the outcome of this reaction next day. So it's a lower synthetic temperatures, which allows us to target those kinetically stabilized phases. The reactions are short. We also can target particular composition in the compositional phase space. And another added feature that we have the hydrogen gas released, and it's particularly important since we don't want to have even traces of the oxide present. So this allows us to maintain the reducing atmosphere during the synthesis. So this is how we do it. We mix our alkali metal hydride precursor with transition metal and metalloid, either antimonite or boride. We then mix them well, and then the load mixture into the niobium or tantalum tube, because similarly to elemental alkali metals hydrides are very reactive and they would attack silica. So once this niobium tube is sealed, we put it into the specially designed silica reactor, which goes then into the high temperature furnace, which can be programmed. So the need for this silica reactor is that's because we have the hydrogen gas evolved, which can diffuse through the niobium tube. However, to prevent the pressure buildup in the sealed silica tube, we use silica container with a check valve, so hydrogen can diffuse out, but air or oxygen cannot diffuse in. So once we know the outcome, we then can screen the phase space, compositional phase space, quite precisely. So this is our sort of experimental workflow, because composition is oftentimes a big unknown. If you want to discover a new compound, we don't have a ways to conclusively predict the composition of that new compound we are targeting. So we try some random composition from the compositional phase space via our hydride synthesis. If we're extremely lucky, we will produce pure new phase, and then we can perform the crystal growth from elements to determine structure by single crystal X-ray diffraction. But oftentimes it's not the case, so we would produce a sample with which may contain a new phase with a known impurity. So then the next question is, so the composition was, let's say, pretty close. So what about the temperature? Yeah, so then we use high temperature X-ray diffraction to see at what temperature this new phase is stable. So then we can optimize our synthesis temperature and perform this cycle again. In some cases where the crystals are not available, crystals for single crystal X-ray diffractions are not available, we then can determine the structure from powder X-ray diffraction. And we also use other methods to determine the compositions of our phases. So for instance, SCM-EDX to determine the composition of the phase. Then once we have a better understanding of what our next composition we want to target. And today I'm going to tell you 2 or maybe 3 stories, if I have time, where we made several discoveries of the ternary compounds in the systems containing alkali metals, sodium or potassium, and then zinc and antimony, or zinc and bismuth, if I happen to have time. So we represent the ternary compositions by those triangles. So you would see several of them in my talk. So basically the edge of each triangle corresponds to the binary phase diagram. Yeah, so here would be the binary phase diagram between potassium and antimony, and then we can put the compositions of the binary phases on the edges of that triangle. And then within the body of the triangle, we put the compositions of our ternary phases. For instance, right in the middle of the triangle would be the composition of 1,1,1 phase, or compound containing 1 potassium, 1 zinc, and 1 antimony metal. And before we started research in these 3 systems, there were only 2 compounds pictured here in those 2 systems, and they have composition 1,1,1, noticeably because of the difference in the ionic radii between sodium and potassium. The structures of those compounds are quite different, even though the composition is the same. Nevertheless, there were only 2 compounds in the systems containing antimony, and none of the ternary compounds in the system with the bismuth. So so those systems are very underexplored, as you can see. But another reason to look into this system was that we hope to discover new thermoelectric materials, because in literature there are several examples of the antimonide compounds with the complex crystal structure, which do have high thermoelectric efficiency. So for the good thermoelectric material, we want to have a material which is a good electrical conductor, so narrow gap semiconductor ideally, but it's also very poor thermal conductor, similar to the glass. Yeah, so having those 2 sort of contradictory properties in one compound, this constitutes the challenge of the discovery in new thermoelectric materials. And so the thermoelectric materials, they are used for waste heat power, for generation of power from the waste heat, because in the applied heat gradient, thermoelectric materials generates power through Seebeck effect, but it can be also used for cooling, for efficient solid state cooling without freons, by using Peltier effect, because if you apply current to the thermoelectric materials, we can get the temperature gradient where one side of it becomes cooler than the other one. So there are a couple of applications listed here already for the thermoelectric materials. However, we still want to increase the efficiency of the thermoelectric materials to make them widely available. For instance, when this way, the thermoelectric materials can be used in our cars, because about 60% of the energy generated by combustion engine is wasted in the form of heat. So if you find a way to harvest that heat and transform it into useful electricity, then this would make our cars much more efficient. So let me start with sodium zinc antimony system. As I said previously, only one compound has been reported in this system. So we've tried our hydride synthesis, and already this composition gave us a new compound with 143 stoichiometry. But then we were curious, what is the best synthesis temperature to make this compound, and so we brought the sample of it to the Argonne National Lab, and here we've collected powder X-ray diffraction data by increasing the temperature, and surprisingly, at a temperature of 736 Kelvin, we saw the drastic transformation of the powder pattern into something else. And then further heating gave us this 111 compound, this thermodynamically stable compound. And then on cooling, we did see that new compound coming back before it transforms back to the synthesized sodium zinc antimonide at 720. So we were very excited, but also very curious to how we can stabilize this, what at that time looked like a high temperature polymorph of this 143 compound. So we targeted that composition and we did quench it from 800 Kelvin. However, we didn't see the formation of this high temperature phase. So we've tried various routes, and this was until we perform our reaction in the silica. And the reason for it to work is that there is the side reaction between sodium metal and silica, which allows us to access the sodium deficient composition. And after we determined the crystal structure of that high temperature phase by using single crystal X-ray diffraction, we realized that it's sodium and zinc deficiency are both needed for the successful synthesis of this high temperature phase. So despite very similar compositions, they're not true polymorph of each other because this composition is similar, but still not the same as 143. So this phase, this high temperature phase, is stable in the narrow temperature range, but it also needs this precise composition, particularly sodium and zinc deficit. Yeah, so, and then once we provide this deficit, we can also make it via our hydride route. And remarkably, those compounds, again, very structurally similar, compositionally similar, they are structurally very much different, and also the electronic structure that, for instance, electron conductivity is very much differs by the several orders of magnitude. Again, it's a structure which determines the properties of the compound. So with this initial success, we were curious on whether other compositions are available. And so for that, we again brought this high temperature phase to the Argonne National Lab. And upon heating, what we observe is that at certain temperature, we start to see new diffraction peaks, which cannot be assigned to something else. So in this particular system, because the high temperature diffraction experiment performed in the silica tube, we again have a method to to slightly shift our composition toward the sodium deficiency, because sodium really like to react with silica. So we start with this composition, which is close to 143, but then upon heating, it's not only temperature which is changing, but also the composition. So basically, if you want to represent this with our compositional diagram, we start with 143 room temperature phase. Upon heating, there is some sodium and zinc elimination, so we get to that high temperature phase. And then if we start here with in the composition which is already deficient in sodium and zinc, further heating allows us to shift in composition toward even less sodium and zinc. So with this composition here, we haven't tried synthetically, but we get to it by heating. And so that composition upon cooling gave us, a couple of binaries, but also an indication of the new ternary phase, or maybe even 2 of them or 3 of them. Well, then we did the screening with the hydride synthesis by targeting a specific compositions from this region. And what we have found out that indeed there are 2 new ternary phases. One has 1,3,3 composition, another has composition close to 1,2,2. And so those phases, they're very structurally complex, but they still have the fragments from that binary, as well as this ternary 1,1,1 phase. So for instance, here highlighted in yellow, you can see this H-sharing tetrahedra of zinc with antimony in the corners. So, and this fragment is present in the 499 phase, as well as in 133 phases. However, the structural complexity of those 2 phases is achieved by inserting a vertex-sharing tetrahedra, as well as the presence of this H and vertex-sharing tetrahedra units. And so this gives a very complex zinc antimony framework with sodium cations filling the space within, like, the channels of that framework. And again, with these compounds, I want to highlight our hydride synthesis because of this good, excellent mixing we can get by using the powdery hydride precursors. We can really target the specific compositions, because those 2 phases, they are sort of similar in compositions. Yeah, if we plot them on our compositional triangle. So here, if you try the reaction from elements, sodium and zinc and antimony in a 499 ratio, we would get multi-phase products, and the sodium zinc antimony would be one of the major phases, as well as the antimony, elemental antimony. However, the reaction from using hydride would give us almost pure sodium 4 zinc 9 antimony target phase. And then similarly with the 133 phase, so the reaction from elements gave us the very multi-phase sample. Zinc antimony, the binary one, is one of the impurities, as well as the other ternary impurities. But the hydride route allows us to target that specific composition and make a pure sample, which then can be used to measure the properties of those compounds. So by using hydride route, we also discovered the sodium-rich ternary phase, pictured here, sodium 11, zinc 2, antimony 5. It's very, because of it's very rich in sodium, it's very air sensitive, so very hard to characterize. But overall, with this hydride method, we really open up that phase space and discovered 5 new ternary compounds which were not previously accessible by using synthesis from elements. Now I want to, how I'm doing with the time.
Yeah, you still have 10 minutes or so.
Oh, okay. So I want to talk about the potassium system now. Similar situation we have. So 1,1,1 compound was the only one before we started looking into that system. And then by using the hydride route and trying different compositions, we discovered this compound 8-X, so potassium 8-X, zinc 18 3 plus 3X, and antimony 16, which is so compositionally this phase is roughly close to 1:3:2 ratio. This is a zinc antimony framework consisting of the H and edge and corner sharing octahedra of zinc, and then with the potassium filling up the channels. And of course, this is not the real structure, but rather idealized structure, because in the 14% of the cases that potassium cation is replaced with zinc triangle, which is located right in the center of that channel. And we use the similar approach, and here, similar to the sodium system, but rather than randomly screening all of the compositions, we use the formation energy predictor, which so we can calculate the formation energy for any given composition within this ternary system, and this energy predictor uses the machine learning approaches to predict the formation energy using the DFT calculated formation energy training set. And it is, as a chemist, we should take it with a grain of salt, but at least it gives us some idea of what other compositions we can try. So for instance, the low formation energy suggesting that there might be a ternary compound stable might be found here as well as in this area. So we've tried the composition over here, and indeed there was an indication for the new phase with a very complex crystal structure. So we did some screening, compositional screening, but by trying different compositions till we figured out what is the composition of the phase by using also SCM-EDX. And so this allows for discovery of that very complex compound, potassium 58, zinc 122, antimony 207. So very complex composition and the structure. So it turns out to be a clathrate structure where we have the potassium zinc antimony framework, which built up the polyhedral cages of different types. And it's a zinc antimony framework, and then potassium filling up the cages. Yeah, and this compound is so special because it's not only the first clathrate compound in this system, but it's also the special clathrate type. So among the reported clathrate types, our was a special one, and no examples have been reported. So we call our clathrate 11 because the rest of the clathrates have been reported previously. So, okay, in the interest of time, I'm gonna skip this part because we again use the high temperature X-ray diffraction to pinpoint the suitable synthesis temperature. And it turns out that our clathrate actually decomposes above 550. So we really need to lower temperature to synthesize this clathrate. Now, this is a very beautiful crystal structure of that clathrate. So there are 3 types of the cages in the structure. It's a 24 vertex cage, zinc antimony made out of zinc and covalently bonded zinc and antimony atoms, and those cages are filled with a single potassium cation. And then those cages come together with the 20 vertex cage. And then we have to add the even larger 28 vertex cage, and potassium cation is really quite unhappy in this because the cage is too large. So it is rattling inside the cage. And then we add 2 more types, another 20 vertex cage and the 23 vertex cage, which is not seen in other clathrate compounds, which make this clathrate even more special. And so this would build up the whole 3-dimensional structure of our clathrate. So we use transmission electron microscopy to confirm the structural model we obtained from single crystal X-ray diffraction. However, and it was nicely confirmed, yeah. So turning to the properties, So as I mentioned previously, for the thermoelectric material, we want to have a material which is a good electrical conductor, yeah, narrow band semiconductor, and we do have it here with this material. But we also want to have the material which is a poor thermal conductor, the material which has very low thermal conductivity, similar to glass. And this is indeed what's happening with this classrate compound. It has this extremely low thermal conductivity comparable to the glass SiO2, amorphous SiO2, and so we think that this is due to the complexity of the structure, but also due to the rattling of the potassium cation inside these large cages in the classrate structure. So we need to further optimize and lower resistivity to achieve a good thermoelectric performance, but this can be done via doping, and we are currently working on that. And so in the interest of time, I'm going to skip the bismuth story. Just want to briefly say that we did discovered 3 new compounds in that system, but the bismuthides are typically are less structurally diverse than the antimonides. And I want to change gears here and now talk about the boride system, particularly lithium-nickel boride system. So where several ternary compounds have been previously discovered. We also tested our hydride approach, and we can make all 3 of them. However, if you want to target new compounds, the question is what compositions we want to explore. So we use our collaborations with theoretical chemists, and they, by using adaptive genetic algorithm coupled with DFT calculations, they predicted the equimolar ternary compound, lithium-nickel boride. They not only predicted this composition to be stable, but they also gave us an idea about the structure that compound might have. And to our greatest surprise, we've tried in the lab and obtained the powder pattern, which is in a close resemblance with the predicted one. Yeah, so this is really a remarkable way of discovering new compounds. Yeah, so we knew its structure before we made it in the lab. However, of course, the reality is often more complex than the prediction. So theoretical methods can predict this room temperature polymorph, but if we increase the synthesis temperature, the structure transforms to the high temperature polymorph. And the difference, so first of all, it's a layered compound, which is very rare among those borides. Secondly, it has a lot of lithium stored between the nickel-boron layers. So we have the nickel-boron layers with a different topology depending on whether it's a room temperature or high temperature polymorph. And then we have a lithium layer sandwiched between those nickel-boron layers. And lithium layer adopt also different configuration depending on the polymorph. And again, we confirm it with scanning transmission electron microscopy. And additional reason why we were very excited about the discovery of these layered compounds is that, well, I guess you all are aware about the rise of the graphene as a layered, as a single layer of carbon, as well as the many other two-dimensional materials among the nitrides, sulfides. And so if you want to target the borides, typically we don't have the good precursor. And our discovered lithium-nickel boride is one of the possible precursors to synthesize two-dimensional borides called mabins. And theoretical predictions suggest that those mabins can find many applications in batteries, magnetic devices, and electrocatalysis. And so basically, we want to have a good layered precursor where we have a transition metal, boron, and alternating with a layer of the secondary elements, which would be easy to remove. Yeah, and even though it is all good on paper, there are still no report on synthesizing of those two-dimensional ambeans, two-dimensional borides. But one of the possible ways to make it is to use the similar approach which was previously used to synthesize two-dimensional carbide materials. So we can do this by using tapochemical deintercalation. So this method provides very mild reaction conditions. It's typically done at room temperature, and it's a kinetically controlled pathway. So we remove, so for instance, if we start here with titanium aluminum carbide, which has this layered structure, we can remove the layer of aluminum by treating this material with HF. Yeah, so in our case, we, instead of aluminum, we have lithium, which presumably should be even easier to remove. So we've attempted it by exposing our material to air at room temperature, and we did see change in the diffraction pattern. So we basically see the disappearance of the diffraction peak corresponding to the interlayer distance between nickel-boron layers. So this suggests that with, by leaving our material in air at room temperature, we can deintercalate lithium layer. And we do see the same for the high temperature polymorph. And interestingly, the similar change in powder pattern is observed when we expose our material at room temperature to water, ethanol, and even diluted HCl. So we were curious to see whether that all of the lithium can be removed this way. So we used solid state NMR spectroscopy for both lithium and boron, and with increasing the exposure time, we do see a change in the peak intensity corresponding to the lithium in the structure of our layered lithium nickel boride. And then after the washing of, and we do also see the increase in the peak corresponding to the lithium oxide. So when material is exposed to air, lithium is going out and form lithium oxide. So we do see the increase in the peak intensity. And then once this sample is washed with water, we only see the deintercalated material, and particularly the lithium in this the intercalated material. And there is also a change in the boron environment. And again, similar behavior is observed for the high temperature polymorph. But this data also suggests that our lithium is not fully deintercalated from the layered structure. So we need to use more advanced characterization methods. So we use scanning transmission electron microscopy, which allows us to see that the layered structure is still preserved. However, there were some changes the material undergoes upon the intercalation. So we do see that fragment where one nickel-boron layer alternating with one lithium layer still preserved in some cases, very minor cases though. However, the most abundant motif is where we have two nickel-boron layers which form this nickel to boron 2 fragment, and those layers are now alternating with the lithium layer. And finally, we also see the fragment, the third fragment, where we have 3 nickel boron layers stacked together and alternating with a single lithium layer. So upon the intercalation, we produced a remarkable layered material which has ordered crystalline layers. However, they are there is no order in the stacking direction. Yeah, so they stack quite randomly, even though each of this layer is perfectly crystalline.
So Julia, we're just about out of time.
Yeah, so let me take just 1 more minute here to
Sure.
wrap it up. Okay. So still, scanning transmission electron microscopy didn't give us the information about the precise information about where the atoms located. So we used X-ray pair distribution function. So we've collected the data at APS, and we do see that upon the intercalation, the local structure of the nickel-boron layer doesn't change a lot. So we use 3 methods in zinc. Our initial models came from STM. Then we optimize them by using DFT calculations and then refine those models further with the X-ray PDF. But because we use X-ray PDF, we can locate the positions of the heavy atoms, nickel in this case. So we use the DFT again to get to optimize the positions of the light atoms such as lithium and boron. And so this, using those 3 methods, allows us to determine the fractions of molar fractions of each substructure, and the calculated formula, which is agrees very well with the compositional analysis performed by ICP mass spec. So we get a very good fit of the data by using all 3 models simultaneously, and we now also can determine the interatomic distances and precise location of atoms within each model. And the same, similar for the high temperature polymorph, use the same approach. And so by using those methods, we determine the process, the intercalation process, which we call it a Ziploc principle. So when 2 nickel boron layers and with the lithium sandwich in between, so the lithium the lithium atoms come out to form lithium oxide, and then the Ziploc closes to form that nickel boron layer substructure with the 2 nickel boron layers. And to wrap it up, I want to say that the parent compounds are temperature independent paramagnets, but the intercalation induces the magnetic odor at low temperatures. At temperatures below 24 Kelvin, we do see the magnetic transition, and this magnetic transition is of the spin glass type. We perform some AC susceptibility measurements to determine it. So our materials, because of this disorder associated with the staking of nickel boron layers, our materials behaves as classical spin glasses. So the take-home message from my talk would be that the solid-state synthesis is so hard, we should use all the help we can get. Yeah, we should use theoretical prediction about the structure. We should use high temperature X-ray diffraction to see what materials are stable at particular temperature. And so the hydride synthesis is fast and it's very it allows us to target a specific composition, so it is perfect for that exploratory synthesis. And so by using hydride synthesis, theoretical predictions, and high temperature X-ray diffractions, we were able to discover several new compounds. And with this, thank you for your attention, and thank you for giving me this opportunity.
Okay, thank you. What a wonderful talk. Amazing work. So we have other sessions starting in about 5 minutes, but we can take a couple of questions. So one question from Jennifer: excellent talk, Julia. Beautiful detective work to discover new phases. I'm wondering about the safety of the reactions. Does the extra tube with the check valve, I think that probably is, always work to release the H2 and avoid explosion?
Yeah, thank you for the question. Indeed, safety should be a very, strong emphasis on the synthetic work we do. And we've never had this reactor with a check valve failed, even though during my postdoctoral appointments, I had a couple of instances where the sealed silica tube exploded. I mean, no one got hurt, and we kept our furnaces inside the fume hood, so it was all safe. However, to prevent this, to prevent this, we invented this. We designed this reactor with a check valve. But it's of course, it may become sort of dangerous if we scale up our reactions. Yeah, so and when we report our synthesis, we always emphasize what is the total mass of the reactants we are using, again, to mitigate any possible safety concerns. But the short answer would be we didn't have any failed experiments with this check valve reactor.
Well, that's good. At my university, that would have been weeks of paperwork if something like that happened.
Well, I'm sure at our university would be the same. Yeah.
Okay, so just very quickly, have you tried stronger oxidizers like Br2 or NO2-BF4 to remove more lithiums, or electrochemical delithiation to high voltage?
Yeah, thank you for your question. So we've tried electrochemical dilithiation, and it did work. However, after the dilithiation, the material, it's not reversible. Yeah. So the material becomes very amorphous, very hard to characterize. So, and I think we think that this is because once the lithium is taken out, those nickel boron layers, they form strong bonds, and then the material the lithiation is not reversible. However, with the other, your other suggestion, no, we haven't tried that, and perhaps we should.
That's great. We're running just about to time. There are a couple of more questions in the chat. Julia, I don't know if you want to hang around for a few minutes and maybe you can.
Oh, absolutely.
Suggest those in the chat. And I understandable if people need to go and join other sessions as well. Can you see the chat, Julia? There's Dina Oren says, please read this for me. Congratulations on the award. Would these processes be used for larger scale preparation of materials? And if so, is there a way to utilize the byproduct H2? And is that even valuable?
Well, yeah, excellent question. So technically, I think it is possible, for the larger scale reaction, you increase the size of the reactor as well as the size of the niobium tube. So the hydrogen, it diffuses through niobium, but it's also some of it reacts with it, because we do see that the niobium tubes becomes very brittle after the reaction. So this might be due to the formation of the hydride. So I'm not sure whether that, utilizing the evolved hydrogen for, other needs is feasible. However, I envision that the scaling up might be possible, even though not going to be not an easy process. Yeah, but I envision it might be possible.
Well, that's terrific. So I think the other comments were basically congratulations and saying how clear and wonderful your talk was, and very impressive work that you're doing. Thank
you so much. Thank you for.
Thank you again, and thank you to the audience. And I hope we will see you in person very soon at the next meeting.
I hope so too.
Okay, good.